Good day, folks. Welcome to my YouTube channel. Today I'm going to do the work energy and power question. It's going to be based on energy, right? It says a pendulum bulb with a mass of 5 kg is held stationary. That's very important. That means the initial velocity is 0. Here's the pendulum bulb. The pendulum bulb is this one. The block is this one. So it's held at rest, which is the initial velocity is 0. Now it says at a height h, meter above the ground. So there's a height there. When it's released, it collides with a block of 2 kg, which is stationary. So when this pendulum bulb is released, it moves down and collides with this stationary block, which is its initial velocity is 0. That's the initial. This is before collision, right? Now it says a bulb swing past A, which is it swings, it kicks this one and it passes A, which is after collision it reached that point, right? And comes to rest momentarily. So when it swings up again, which is to this point, it reaches that height, which is quarter h, and then it rests momentarily. So that means the velocity there, while it is at rest momentarily, it's 0. Now it says here, the diagram below is not drawn into scale. So the collision, it kicks this block and it moves to the right with a velocity, which is that velocity. It's a velocity after collision. Now it says here, immediately after collision, the 2 kg block begins to move from point A to point B at a constant speed of 4.95. So the velocity of this is 4.95 meter per second. Now it says here, ignore the frictional effect and assume no loss of mechanical energy occurs during this. So the mechanical energy here is conserved, so there's no loss of energy. In fact, the energy has been lost and it will be gained as well. So the energy is maintained. So here the energy will be lost by the bulb through the gravitational potential energy, because as it moves down, the height is decreasing. That means the gravitational potential energy is decreasing, so it loses energy, but as soon as it hits this object, this one will gain, because its velocity is 0. The kinetic energy is 0 here. Its kinetic energy is 0, but as soon as it's kicked, or it collides by the bulb, as soon as the bulb hits this one, it will start increasing the velocity, which is the kinetic energy will increase. So the energy that has been lost by this one through gravitational potential energy, it will be gained by the block through the kinetic energy. Okay, I'll show you that later. Now 5.1.1, it says calculate the kinetic energy of the block immediately after collision. The kinetic energy of this after collision. So we have the velocity there. So 5.1.1 will say kinetic energy after is equal to half mv final squared, and then it's half the mass of the block. It's 2, and then we times by the velocity, which is 4.95 squared, and then the answer for that, it will be 24.5 joules, right? That's the kinetic energy of this one. So this is the kinetic energy that this one gained after the bulb lost the kinetic energy. I hope that makes sense, guys, and it's very important to understand that. Okay, now let's go to 5.1.2. It says calculate the height. So we want the height, which is this h. Guys, this is quite tricky question to do, but it's very important to understand. Guys, I'll start with an easier way. And then I'll show you the difficult way. It's not difficult, but it's longer. It's longer. It requires you to understand. So as I've mentioned, guys, before, that This one, this system, the energy here is what is conserved, right? So this one, the pendulum bob loses the energy through the gravitational potential energy, because its height, it's h there, and then it decreases up until zero, which is it loses the energy through gravitational potential energy. There's a change in gravitational potential energy from that to that. When it's here, there's no height here, it's zero. And then this one, it has no kinetic energy when it's here. So as soon as it collides with the bulb, it will gain the kinetic energy. So the energy that has been lost. So what are we going to say? We'll say the energy loss by the bulb through the what? The gravitational potential energy, right, is equal to the energy gained. The energy gained by the block through what? Through the kinetic energy, right? It's very important, guys, to understand that. So the change in gravitational potential energy here, its energy lost is negative, so it's going to be change in gravitational potential energy, and is equal to the change in what? In kinetic energy, right? So it's going to be mgh final minus mgh initial, and then the kinetic energy, it's half m that. And then let's substitute, guys. This side, the energy lost has been lost through the what? The bulb. So it's going to be the mass of the bulb, it's 5, and the mass of the bulb is 5, right? Yeah. And then we times by 9.8, and then open bracket at the height final of the bulb. Guys, the height final is the quarter. This is the height initial, which is h, and the height final is that one. So the height final, it's the quarter. It's 1/4h minus the height initial is just h. This is the height initial, and this is the height final. Close bracket. And then in this one, this is the bulb, and this is the block. The mass of the block is 2, and we multiply by the final velocity. This was the final velocity. The initial velocity of the block, it was 0. So the final, it's going to be, what is the final? It's 4.95, the final velocity square, minus the initial, it was addressed at 0. So if you punch in the calculator, this side, you see half times that eventually it gives you this. You calculated the kinetic energy of that one, so it's going to be 24.5. And this side, so when you say negative 5 times 9.8, it's going to be negative 49, and then you times by the quarter. Okay, let me close the bracket. And then half, quarter minus the half. Okay, let me punch it in the calculator. A quarter minus 1. Guys, remember, this is a quarter minus 1. These are the like terms. So it's going to be negative 3/4h. I hope you get that math. And then you say 49 times by quarter. So it's going to be 36, because it's a negative times negative. It's going to be 36.75 h equal to 24.5, and then we divide by 36.75, and then so it's 24.5 divided by 36.75. Yep. and then the height here is 0.67 right, meters. That's the height h, right? Let me show you the longer way, but it's not difficult. Let me show you the longer way. Let me use this one now. Guys, I will use this is a closed system, right? I will use the conservation of mechanical energy. I will say the mechanical energy before is equal to the mechanical energy after. But you need to remember, before there are two objects. There's a bulb and the block. So this one, it has its own mechanical energy, and this one has its own mechanical energy before is equal to the mechanical energy after, which is the mechanical energy of this plus the mechanical energy of that. Okay, let's do it. This one, it requires space. I'll say the mechanical energy before is equivalent to the mechanical energy after. Right. Now, guys, you need to pay attention here. So we'll say the mechanical energy of the bulb plus the mechanical energy of the block. This is when before, right, as I've mentioned, and the mechanical energy of the bulb plus the mechanical energy of the block. It's block. And this is after. Let me fix this error here. This is supposed to be block, right? Now, guys, we know the mechanical energy. Let me just put square bracket. We know the mechanical energy. It's going to be the mechanical energy here. It's going to be mgh plus half mv initial square of the what? Of the bulb. Right? Plus the mechanical energy here. It's mgh plus half mv initial square of the what? Of the block. This is when, this is before, equal. We're coming here. It's the mgh plus the half mv final now, because it's after. This is what? This is the bulb plus the mgh plus the half mv final square. This is the what? This is the after, right? Now let's go and substitute now. This is when it's going to start to be easy. Now, after doing that, guys, you don't have to do all these things. You can just start from this one, or you can start from this one. As long as you have the formula, or from this straight to the substitution, right? You don't have to show all these. I'm showing you this just for you to understand. You don't get mark for all these. You get mark for any of this. You just one mark for this or that, right? Just one mark. Right, let's substitute now. Now, guys, you need to think very carefully. This is before. When we talk about before, we're talking about here, right? Let's look at the bulb specifically. The gravitational potential energy of the bulb. What was the gravitational potential energy of the bulb? It has the gravitational potential energy here, but we do not know the height here. It has the gravitational potential energy because it has a height. So the mass is what? It's 5. It's 5 times 9.8, and the height we are not given. It's h. Okay. Plus, it was held at rest here. We're here. So we're in the bulb. We're here. It was held at rest. So its velocity is what? Is 0. That means the kinetic energy is going to be 0. So let's close it. Plus, this is the bulb. And then we are in the block. The block before it was at rest. So the velocity, it was 0, and the kinetic energy is 0, and the height is 0. That means the gravitational potential energy is 0. So here it's going to be 0 plus 0, and that's the block. You see how easy. And then we go, this is after the bob after here. So we were told the bob, when it's here, it was momentarily at 0. It came to rest momentarily. So this is going to be and the height, the velocity there it's 0, and the height it's quarter. It's at a quarter height, right? It's quarter height. So the gravitational potential energy there, this is the bob. It's 5 times 9.8, which is mgh, and then the height is what? It's quarter. It's going to be quarter h, plus the kinetic energy is going to be 0 because it was momentarily at 0. This is the bob, right? Plus the block. Now we are in the block. This is the block, right? Forgot to write here block. This is the block. The block after, it has no height, so it's in the ground. Its gravitational potential energy is going to be what? The mgh is going to be what? 0. And the kinetic energy here, after we calculated, it was that 24.5. So was it 24.5? Yeah, 24.5. This one, right? Become easier. Yuppie. So it's going to be 4 times 5, 4 times 9.8, 5 man. 5 times 9.8, it's 49h. 49h. That's all you have this side. Let's move it here. It's going to be equal. And then we're going to have 5 times 9.8 times quarter. So it's 5 times 9.8 times by 0.25, which is the quarter. So it's going to be 12. It's going to be 12.25 h plus this. It's 24.5, and then we transpose. We're going to have 49h minus 12.25 h is equal to 24.5, and then your h is going to be 0.67 meters. That's easy, just like that. Okay guys, I hope this is making perfect sense. And the other part of the question, which is 5.2, let me just move it here. Okay, 5.2, it says, now the block moves from point B at a velocity of 4.95 up a rough. When they say rough, that means there's a what? Friction now. A rough inclined to point C. The speed of the block at point C, it's 2 meters. So this block, it moves here from here with that velocity and moves up a rough surface and reaches that point C with the velocity, which is going to be final, which is 2 meter per second, and this one will be the initial, right? Of course, the velocity decreases to that due to friction. Now it says point C is 0.5 meter above the horizontal, which is the height there. Guys, I'm sorry about the noise. It's my neighbors. During its motion from B to C, its uniform frictional force acts. So there's a frictional force that is acting here. Guys, it's very important to understand as well. While it's moving here, what are the forces acting on that? I'll draw the free body diagram quickly of the forces that are acting there. While it's moving up there, there's no force applied. There's a gravitational force, which is the FG parallel, and there's a frictional force that are going there. Those are the only force that are acting there. Now, 5.2, it says state work energy theorem. The work energy theorem, it says the net work done on an object is equal to the change in kinetic energy of an object. Still to the exam guideline when it comes to that. Now use energy principle to calculate the work done by frictional force when 2 kg moves from point B to C. So we want the work done by the frictional force. So what are we going to use there, guys? I'm going to use 5.3, the energy principle. So the energy principle, guys, I'm going to use the this energy principle, which is the work done by non-conservative. So then the non-conservative force that is acting while it's moving here is the frictional force, which is, I'll say, work done by what? Frictional force. That's what I want. And then the kinetic energy is going to be half mv squared minus mv initial square, close bracket, and mgh final minus initial, right? So now I'm substituting. It's going to be the mass of the block, it's 2, and the final velocity, it's 2 squared. The initial, it's 4,95 squared. Guys, when you put in the calculator, don't square the negative, you just square the number only. Square plus 2 times 9.8, which is mg, and the height final, it's 0.5. This is the height initial, and this is the height final. The height final, it's 0.5. The height initial is 0. It's 0 height there. So punching that in the calculator, the answer that we get there, it should be negative, because the work done by friction, it's negative. So the answer there, it will be negative 10.7 joules. Hope, guys, this question makes sense, and if it doesn't, go back and rewind the video up until you get it. Cheers, bye.